All right, last lecture we looked at the NGSS. We very briefly looked at navigating it. There was the worksheet, looking at finding the different parts, the SEPs, the DCIs, the CCCs. And now we're finally getting into what's some of the material that you'll need to teach your students. So measurements and the metric system. But first, what is a teacher-focused notebook entry? So in your notebook, which if you look ahead to week 4, in the Canvas modules, you'll see that there's a notebook check. So in the notebook check, what I'm going to be looking for is essentially, did you take notes during each of the lectures in some form? Like, did you take a reasonable amount of notes for the amount of stuff that we talked about? Is it related to the stuff that we talked about? Did you do the ball drop experiment? Did you do the building the paper cards? There's also going to be some stuff that's teacher focused. So oftentimes when you're in a class, because you're students, you're acting as a student, because that's what you are. And this was also true during the ball drop activity and the index card activity. But we also want you to be thinking with your teacher hat on, because you want to be teachers. That's why you're in this class. And so we want to start thinking ahead. How would I think about this as a teacher? And I had some questions for us last week of like, what did we notice about the experiment? What were some good things? What were some bad things? Things like that. So we want you to swap your student hat for a teacher hat and think about how would you prepare this lesson for your future students? Because a lot of the stuff that we're going to be learning, maybe all the stuff that we're going to be learning, you will also have to teach students. And that's, I think, where this science teaching practicum nonsense comes in. It's not nonsense, it's good, but we didn't know about it. So this next slide is going to walk you through 10 aspects, 10 things to think about if you were teaching this lesson for your future students. When you do this, it's helpful to focus on one grade level, so thinking about kinder, first, second, third, fourth, fifth, and gearing all of your answers towards that grade. This doesn't mean that you have to consider all of these, but some things that you could think about. So teacher focus for notebooking. Some things you want to be thinking about. What are some keywords? Connecting some of our language. So what were some important terms or words? These could be vocab that you expect your students to know, or new concepts that you're introducing. What are some relevant physical science concepts or theories? It's like with the ball drop experiment, is it age appropriate, grade appropriate for you to be thinking about gravity, resistance, the bouncing action? What are some relevant math ideas? Like, should we graph how frequently it hits the ground, or how long it takes based on how far high up we drop it? Sketching opportunities. Sketching here being drawing. What could you have your students draw up? You want to be thinking about possible student misconceptions. You're almost never going to get all of them, which is awesome. You'll have been teaching it for 5 years, and then suddenly a student will come up with some new way to do something that you didn't expect. So when you're thinking about possible student misconceptions, if you have written directions that you're providing, it can be important to read through it and think, are any of these words, do they have other meanings? Or could the meanings possibly not be clear? Reread and be careful or clear with directions. And from my own personal standpoint, if there are misconceptions and somebody does something a different way, that's okay. Don't, make sure that the student understands, like, no, what you did was totally valid, if it was, right? If they interpreted it in a way that made sense, let them know, hey, that makes sense, but that's not what I was expecting you to do, and then maybe sort of refocus them, hey, do it the way that I wanted you to do it, please. you want to be thinking about, are there some suitable grade or NGSS connections? So this might involve doing a quick scan of whatever grade level you're looking at or planning to teach. Are there any NGSS standards that connect to the thing that you were thinking of? It's also helpful, or it can be helpful, to think about representation. So thinking about gender, culture, other things. Sometimes there's great opportunities to talk about, scientists of color, people that discovered things who were not white men who are dead. That's a lot of the people that we credit with scientific discoveries in the past, but there are other ways that you can bring other people in that maybe will connect more with your classroom depending on what the makeup of your students is. Safety concerns is a big one. How could somebody get hurt? Because we don't want our students to get hurt, so we want to think about, is there a way that my student could possibly hurt themselves? Like if you've got them doing a ball drop experiment, don't throw them. Make sure that you're just dropping them, because if you throw them at the ground, it could bounce back up and hit somebody, or it could hit a thing in the room. The cost for the class. Ideally, we want to be minimizing our budget. So if we're buying stuff, ideally we'd like it to be able to be used multiple times, so that you just go grab it out of the storeroom, or you go grab it out of the closet, instead of single-use items every single class that you have to keep buying. And then if there's any other considerations or concerns, so just anything else that you might be thinking of. So thinking about our ball drop experiment, where there's some keywords or language connections, relevant science concepts. Is there any math that might connect? Is there an opportunity for them to draw? Would you like them to draw something? Wording it so that it's not confusing, thinking about ways that we could for ourselves and maybe to show our admin, connections to the NGSS, that we can loop it in with what they're supposed to be learning, and the rest of the stuff. So when we're doing a teacher-focused notebooking, think of how would you plan this for your students, and these are some examples of things. You don't have to include all of them. Let's put that in red. Don't have to include all of them. These are just some jumping off points. Some suggestions to think about, or about which to think. Questions? So at some point, go back into your notebook and think about our ball drop experiment as a teacher. How would you plan it out for your students? And reference back to this list. Okay, so connections to the next generation science standards, the NGSS. We've got a cross-cutting concept that comes up that's related to measurement and numbers, and that's cross-cutting concept 3, scale, proportion, and quantity. In considering phenomena, things that happen, it is critical to recognize what is relevant at different measures of size, time, and energy, and to also recognize how changes in scale, so small things, big things, proportion, or quantity, the number of things, affect a system structure or performance. So if you have a room of 10 students and you tell them to all discuss amongst yourselves or to chit-chat with their neighbors, they might be able to hear each other. If you have a lecture room with 500 people and you tell them to all start talking, it's probably going to be a monstrous roar if they all actually take you up on that. So there's considerations to take into account when you're dealing with small versus big. and we are going to learn scientific notation. So we're going to have to recall some of our math that we've hopefully learned. So scientific notation. In science, we often use what's called scientific notation, and this is because with our advancing technology, we make measurements that are very, very big, incredibly large numbers that we can't comprehend. We also make measurements that are very, very small, really, really small that we also can't comprehend, and it can also be sort of annoying to include all of the zeros either in front of or behind the numbers that we actually care about. And if we've got more digits, it's easier to accidentally drop a 0 and make a mistake. So when we're dealing with really, really large or really, really small numbers, it can be very cumbersome. It can be very annoying. We're thinking of things like trillions and bigger, or billionths and smaller. So numbers like a number that I just chose. Does anyone know what this number is? It's not like related to a physical thing in reality, just like how would you say that number? It takes a while, right? With really large numbers, it can take us a while to figure out how to say the number because we have to count out, and it helps if we've got some commas in there. So we'd look at the commas. Okay, this comma means that these are thousands, millions, billions, trillions. Millions, billions, trillions. So this would be 1,654,000,000,000. Super large number. This would be annoying to have to write 10 times on a page because we have to write out all these zeros. It also takes us some time to count out all the way over to the place that we're in, which is the trillions. So when we're dealing with really large and small numbers, it can be annoying because we have to do stuff like this. So scientific notation gets around that. It also requires us to have some familiarity with scientific notation. So all scientific notation is a way to write very large or small numbers, we're thinking measurements, in a compact form. So shrinking it down to just the stuff that we care about. When we're using scientific notation, there are two parts. There's two parts to scientific notation. There's this front part. In this case, the example number is 2.468. This is always going to be a number that's between 1 and 10. So it's from 1 up to, but not including, 10. That's the first number. So it can be as small as 1, can't be smaller than 1. It can go up to, but not including 10. So a 9 with as many 9s as you can imagine after it, that's as far as we go. So we're looking for one digit before the decimal. So before that dot, one number, only one number. That's why I said we can't have 10, but we can go to 9 with a lot of 9s after it. So 1, 2, 3, 4, 5, 6, 7, 8, or 9. No zeros in front of our decimal. That's the first part. Then the second part is this times 10 and then raised to a power. It's always going to be times 10, and then in this case 8, that's the part that we would either come up with or we could interpret to switch it into something else. That's the part that changes. The times 10 is always the same, and then the 8 is the part that changes. So that, and then this 8, that's the part that changes. So as a reminder, this little number up in the top right corner is our exponent. And I think there's exponents showing up, yes, on the next slide, sort of. So we can sort of see down here at the bottom some of our exponents. I'm leaving the top part up in case people are still writing that. So at the bottom, 10 to the 0, 10 times 10 0 times gives you 1. That can be confusing. Anything raised to the 0 power always gives you 1 for reasons. 10 to the 1, 10 times 10 one time, just 110, so it returns the same value. 10 to the 2, the exponent 2 means multiply this number by itself 2 times. So sliding away, we've got all the exponent means the middle dot is our multiplication symbol, or that's how I'm using it in this case. So 10 to the 2, 10 times 10. That's our first 10, that's our second 10. We've got 2 10s, 10 times 10. 10 to the 3, throw another one in there. 10 times 10 times 10. We'll use the x's for multiply this time. So the exponent tells you multiply that number, whatever that number is, times. Usually it's whole numbers, 1, 2, 3, 4, 5, counting numbers. We also can have negative numbers. What the negative means is divide instead of multiply. So 1 divided by 10 for 0.1. Or 10 to the minus 2, 1 divided by 10 times 10. Or 1 divided by 100, which gives you 0.01. That's sort of what the exponents are doing, what the scientific notation part does. So the scientific notation part, that second part, the times 10 to the 8 in the previous slide, is telling you super big number, 100 million. So whatever that number was, hundreds of millions. So that gets all of our zeros in there. But it's faster than writing this out. It's also a lot faster to read. Typically, when we're dealing with scientific notation, we just plug it into our calculator. So if we want to write a number in scientific notation, there's a couple of steps. First step, we want to move the decimal point in the original number. So it's located after the first non-zero digit. So move the decimal. So 1 digit is in front. Okay. We will do examples, and you'll also have some to practice. That's our first step. You can move the decimal over to the right or over to the left. You can move it over to the right. Then we want to multiply that number by 10. So we're doing this times 10 part that I said was always going to be the same. We're doing times 10. And we're going to raise it, or apply the exponent of the number of places the decimal point was moved. So basically, you'll just be filling in this red blank that I've left there. How many places did you move it to the left or the right? And the sign, positive or negative for that number, depends on which direction the decimal was moved. Positive exponent is bigger than 1. Positive exponent means the original number was bigger than 1. And negative means that it was smaller than 1. I think some of this information shows up on the next slide too. I think typically the most confusing part of putting stuff in scientific notation is figuring out, is it a positive exponent or is it a negative exponent? And again, we'll be doing some practice. So in slightly different words, positive exponent means that the number is very large. So we're thinking 100 or greater, typically. Big numbers get positive exponents. Negative exponents are for small numbers, things that are smaller than 1. Do we have any questions so far about exponents or scientific notation? All right. So example, we want to write this number in scientific notation. So we need to move the decimal place so that it's between, in this case, the 4 and the 2. The 4 is our first number that's not a 0. So we want to move the decimal so that it's behind that number. So we're going to move it over. That's where our decimal goes. So we've got one non-zero number in front of or to the left of our decimal. So we get 4.23. And this 4.23 is the first part of the scientific notation, because I said there were 2 parts. This is the first part. The second part, what's the second part? Times 10, and then some other number. And we have to figure out what that number is. So we've got the first part, pretty easy, 4.23. That's our first part. The decimal place was moved over 4 places. So if we counted over when we did this, they're not really bunny hills, but the loops that I made there, I did that so that that would represent us counting. Usually I'll count it over. So we moved it over 1, 2, 3, 4 places. We'll put some numbers under there like we're counting them. We moved over 4 places. So the exponent's going to be a 4. So at this point, we've got 4.23 times 10. We moved it over 4 places. Change that to a blue underline. So we've got a 4. And then we need to figure out this one last piece of information. Is it positive 4 or negative 4? Negative 4. Why is it negative 4? It's a small number. Small numbers get negative exponents. That's one way to think of it. And so we would give it a negative 4. So our entire scientific notation, 4.23 times 10 to the negative 4 power. You can also remember it if you're moving the decimal place to the right. That means you're going to have a negative exponent. If you're moving it to the left, you're going to have a positive exponent. I think that's a little bit less helpful, because if you get it flipped, it's really easy to get it flipped. I think remembering small numbers get negative exponents, big numbers get positive exponents is better because it relates to actual numbers. Questions about any of the steps that we did there? All right. Some more examples. Please convert these numbers into scientific notation. I'll give you a little bit of time to do this. All right. Who's got the first one? Converting 4,000 into scientific notation. What's our first part of that one? 4. 4 is our first non-zero number, so we're going to move the decimal so that it's right behind the 4. What's the other part of it going to be? The exponent part. Times 10, raised to what power? 3. Positive 3, negative 3? Positive 3, because it's a big number. So you should have ended up with, I don't know why that erased into that way, but 4 times 10 to the 3, what you should have gotten. We don't need to keep any of the zeros that come after it in this particular case. If you take Chem 20 or something, there's instances where you might keep those. We don't have to do any of that. Awesome. So just 4 times 10 to the 3. Times 10 to the 3 because 4,000 is a big number. I would love to get $4,000. Somebody said, hey, here's $4,000. I'd say, that's a lot of money. Are you sure? No, I'm just kidding. I'd take it. Hasn't happened to me yet. What about this next one? 306 million. Big number? Big number, bigger than 4,000. What's our first part of this number going to be? Where are we moving our decimal? Towards the 3, so that it's right behind the 3. So we'd move it over. Normally, if we've got a number that's 1 or bigger, right, the decimal just sits after it secretly. So we're going to move it over 1, 2, 3, 4, 5, 6, 7, 8 spots, so that our decimal now lives behind the 3, and we're going to get rid of all those trailing zeros. So it's after our last non-zero number, so we can get rid of them. So we should end up with a 3.06. There it is, 3.06, and we moved it over 8 places. So it's times 10 to the 8. It stays a positive number because it's a big number. What about example 3? Who's got this one? What would that be in scientific notation? 8.82 times 10 to the minus 4. 8.82 because we moved our decimal place over so that it's behind the first 8. So we get 8.82. That's our number part. And then the exponent part, we moved our decimal place over 4 spots, and that's a small number. So 8.82 times 10 to the minus 4. Perfect. And then the last one would be 5.9. We move the decimal place over so that it's after the 5. So 5.9 is what stays. And then 10 to the negative 7 because we moved our decimal over 7 places. And it's a number that's smaller than 1, so it's a negative exponent. Questions about any of those? Great. Some more examples. Convert these numbers out of scientific notation. So turn these into like standard notation. We didn't talk about this, but let's just see if we can do it. I'm just kidding. These are examples. So I'm going to show you how to do them. And then the next slide has for you to do them. So this number, 2.48 times 10 to the 3. The times 10 to the 3 part is the part that we're really going to be paying attention to for converting out of scientific notation. The 3 in 10 to the 3 means that we move the decimal how many places? 3 places. Is 3 positive or negative? It's positive, so we're expecting a big number. So we want to move it in a way that gives us a big number. So the way that we can move it so that we get a big number, I'm going to rewrite it to the right. So 2.48. If we move it to the left, we'd end up with zeros, 0.00248. That's a small number, right? So we don't want to move it that direction. We'd like to go the other direction. So we're going to move to the right 3 spots. We don't have 3 numbers to move it past. So what are we going to do after this 8? What can we add in there? A 0. So we're going to put in a 0. So 2.48 turns into, times 10 to the 3, turns into 2,480. You don't have to include the comma, but oftentimes we do include that comma. So 2,480. For the next one, 6.123 times 10 to the 6. Again, we're really focusing in on the exponent part, times 10 to the 6. The 6 lets us know we're going to move that decimal place over 6 places. It's also positive, so that means we're expecting a big number. We want to move it to the right so that we get a big number. So doing that also on the right side, 6.123. We're going to move our decimal place over 1, 2, 3, 4, 5, 6 places. And then we have to fill in some zeros. So for all these extra places that we jumped, we're going to fill in zeros. You can also add the zeros in first and then move the decimal place over and then just get rid of any zeros that you don't need at the end. And we get rid of that decimal. So 6, 1, 2, 3, 0, 0, 0. Or 6,123,000 if we add in those commas. And then our last one, 4 times 10 to the minus 5. Looking at our exponent again, because that's sort of the most important part. This lets us know how many decimal places we move our decimal over. Where does our decimal live? In the number 4. There's not a decimal there. Where should it be if we looked at it? Not before? 4 decimal places. So we always have one number in front of our decimal when we're in scientific notation. So our hidden decimal lives right after the 4. This is important so that we make sure that we move it the correct number of places. So it's always going to be after that first number. Most of the time, you'll have other stuff after there, so the decimal will be written. This is a little less likely of an example. So there's our decimal. We want to move it 5 places so that we get a big number or a small number? Small number because we have a negative exponent. So which way are we going to move it to get a small number? Left or right? We're going to move it left. If you're not sure and you're converting stuff out of scientific notation, you can do both, right? You can do both. What if we move it to the left? What if we move it to the right? Which one's big, which one's small? And then pick the one that matches your positive or negative exponent. So we're going to move it to the left 5 places. We're going to need some zeros in front of there to add some space. So I just added a bunch of zeros in front. We want to move it 5 spots to the left. So 1, 2, 3, 4, 5. Our 0 goes right there. And then so that things don't look weird, we're going to get rid of that extra 0 in front. Because it looks weird unless you're like in accounting. Maybe they have some instance where you'd have a 0 there for some reason. Anyway, we get rid of that. We'd rewrite it as 0.00004. And that's what's in the slides. Questions about any of those? All right. Here's some more for you to try. Convert these numbers into or out of scientific notation. All right, so hopefully that was enough time to do some of them at least. All the answers are just on the next slide. Shabam. Answers. Questions, concerns, confusion about any of these, if you want a real quick check. Is that what I got? So our left column is all big numbers. So the exponents are all positive for the 2 that we're converting out of scientific notation. So we end up with numbers that are bigger than 1, big numbers. For the ones that we're converting into scientific notation, they're all big numbers, larger than 1. So we give them positive exponents for the number of places that we move the decimal over. All the non-zero numbers stay there. For these, what we would call interior zeros or internal zeros, those zeros stay because they're placeholders. but we can get rid of everything that's trailing. And then for the numbers that are smaller than 1, the little numbers, if we're converting them into scientific notation, we can get rid of all of the front zeros when we turn it into the number part. And then we give it a negative exponent for the number of places that we moved the decimal over. For the ones that we're converting out of, we have to add zeros in front, and then we shift the decimal place over to the left. All of our non-zero numbers stay in there. And it's nice to have a 0 in front of the decimal because it makes it easier to see the decimal. So I'd recommend when you're converting stuff into standard notation, put a 0 in front of the decimal. Strictly speaking, like, you don't have to if you're putting it into a calculator. If you're not putting it into a calculator, it can be confusing to see all those zeros and not have the decimal between two zeros. So include that front 0. All right, moving on from scientific notation to measurement. We've got feet on the slide, which is gross. Hairy feet. I made lecture slides for my Chem 20 class, and I made sure to find a picture where they were wearing socks instead of having their bare feet out. So measurement is a quantitative observation consisting of 2 parts. Who knows what quantitative means? Very scientific sounding word. Quantitative, the quantit part, quantity. Basically has a number. So quantitative measurements, quantitative values are things that have a number that goes with them. Some quantity, like number of students, oranges, kilograms, potatoes, Mountain Dews, things that you can measure. Thinking of cans of Mountain Dew. Things that you can measure with a number. That's quantitative. The counterpart to that, this isn't exactly relevant to the class, but the counterpart of quantitative is qualitative. So qualitative looks at qualities, so colors, sounds. It's more descriptive. There's not a number associated with qualitative. So that's the quantitative. So a measurement is a quantitative observation, something that we observe, something we measure. It's got a number because it's quantitative, and it also has a unit. What was I doing there? Must have a unit. There are an infinite number of units. We're going to learn some of them. We're going to learn some metric units, but like people, chairs, tables, those can all be units. We're going to be learning the metric measurement units. So some examples of measurements: 20 grams, 32 seconds. So we've got a number part, we've got a unit part. The unit part would be the grams and the seconds. We're going to learn the metric system because scientists at large use the metric system. The metric system is used for measurements. So when we measure quantities, when we take observations, when we do experiments, we're typically going to record our outcomes using the metric system. When we solve problems, typically we're also going to be using the metric system. So the metric system has a couple of different aspects that are shown here. There's more than just these, but for different types of measurements, you can measure length, the distance between 2 places, 2 points. And if we're in the metric system, we're going to be using meters. Meters are about the same, but not exactly the same as a yard. So like this yardstick I'm holding up, a meter, it's the same like order of magnitude as a yard. This is actually a meter stick. So the yard part, a yard comes out to here. So yard's here, meter's here. Meter's a little bigger than a yard. For volume, thinking like soda, because soda often comes in 2 liters. So liter is our unit of measurement for volume. How much space, 3-dimensional space something takes up. Our metric unit is the liter. in the parentheses at the end, that's what we shorten it to. So like feet gets shortened to FT, meter gets shortened to M, liter gets shortened to L. It's important to learn the name of the unit and hopefully what it's measuring, as well as the abbreviation. So unit, and then in parentheses, the abbreviation. Typically, you're going to see the abbreviation part. For mass, thinking pounds and ounces, in metric, we have grams, which gets shortened to G. For temperature, how hot or cold something is, we probably are used to Fahrenheit. And in metric, we use degrees Celsius. So the little plimsoll up here, the 0 that's up high, that's our degree sign, and then the C for Celsius, capital C. For time, it's just the second. So it's the same time that we're used to. So nothing special for time, which is great. So why do we use the metric system? It's universal in science. Everyone in science is going to use the metric system. We might take measurements sometimes in the imperial system or the, what's the other name? There's a couple of different names for the system that we use in the US. We might take measurements in like feet and inches sometimes, but we're going to publish our results or share our results using the metric system. We might report both depending on the context. This also, believe it or not, makes it easier to convert between units. We'll see examples of that. It also helps reduce error in communication of data. If we're always using the same system in science, then if we somehow forget to include a unit, sometimes we can just throw that on. Or if we remember only the number and we don't remember the unit, we're like, oh, we're in science, so it's probably this unit. So it can help reduce some of the errors in communication of data. There's some famous examples of communication errors that cost a lot of money. So a difference between the English system, one of the other names for the system that we use, and the metric system is the conversion factors. So in the English system, if you're converting inches to a foot, there are 12 inches in a foot. For converting feet to a yard, there's 3 feet in a yard. If you're converting yards to a mile, there's 1,760 yards in a mile, which is not a number that we'd probably normally think of. Does anyone know how many feet are in a mile? 5,280. There's 16 ounces in a pound. There's also ounces when we're measuring volume. Does anyone know how many ounces are in a cup? Fluid ounces? It's 8. Does anyone know how many cups are in a pint? It's 2. How many cups are in a quart? 4. How many quarts in a gallon? Also 4. Does anyone know how many feet are in a furlong, which is the distance around a racehorse track? I don't know that one either. But that's also, I think, looped into the English system. So there's a lot of really fun unit conversions, and that's just touching the surface of the English system. In the metric system, how many millimeters are in a meter? There's 1,000. How many meters are there in a kilometer? There's 1,000. How many grams are in a kilogram? There's 1,000. How many kilograms are there in a ton, a metric ton? There's 1,000. Yeah. So it's not always 1,000 in the metric system, but it's always going to be a factor of 10. So it'll be 10, 100, 1,000, a million, a billion, and also the small versions of those. In this case, they're, hello? My iPad's freaking out. We're geeked. Okay, it's just geeked on my end now. That's awesome. Hello? Hello? Pausing. All right, we're so back. So in the English system, they are all different. There's like however many conversions you want to memorize, there's conversions that you can memorize. In the metric system, they're all factors multiples, not multiples, of 10. So like if we're thinking about our scientific notation, 10 to the 1, 10 to the 2, 10 to the 3, 10 to the 4, there was that slide with all that. It's all that. And this is not just within one unit, it's like millimeters and kilometers. It also applies to all the other aspects. So for volume, milliliters, kiloliters, liters, it's also in there. It also applies to mass. It doesn't apply to time. Time's just always the same because it's time. All right, so who uses each of the measurement systems? In red, people that use the English system. Everyone else, the metric system. So it's also nice because we can communicate with the rest of the world. A thing that's helpful about learning some basic familiarity with the metric system, if you're watching like TikTok videos, YouTube videos, from somebody who's in any other part of the world, and they're talking about either how far away something was, how tall they are, how tall somebody that they're interested in was, anything like that, how much food they bought, you can get some sense of what that height, that distance was. If you're completely unfamiliar with the metric system, then you might have to go ask Google, hey, what's this, how many meters in feet and inches? What's a meter 80 in feet and inches? Versus if you have some familiarity with the metric system, you'll know, okay, well that's like 6 foot-ish. Okay, so getting into some of our individual units, length is measured in units of meters in the metric system. Some useful relationships between units of length within the meter system is 1 meter equals 100 centimeters. So centimeters, centi, like cents, like with money. So cents, there's 100 cents in a dollar. There's 100 centimeters in a meter. Same relationship. And then 2.54 centimeters equals 1 inch. That's one of my favorite conversion factors. That's an exact conversion factor. It didn't also always used to be that way, but I'm not going to tell you more about that right now because we're in class. Distract me some other time with that, though. So these are some useful relationships to know. There's also millimeters, which are 1 order of magnitude smaller, meaning move the decimal place over 1 more time from centimeters to get to millimeters. So there's 10 millimeters in 1 centimeter. You're not expected to have all these memorized, by the way. It'd be awesome if you did memorize them. You don't have to have them memorized, at least right now. So we look at a meter stick. The meter stick is slightly longer than the yardstick. You just chop off a little bit. So a meter is about, I think it's about 3.3 feet, and a yard is 3 feet. So it's just a little bit longer than a yard. For measuring mass, the mass of an object, which is slightly different from weight, pounds and ounces measures weight, and mass measures the amount of material that's contained in an object. A pedantic difference. It doesn't make any difference if you're on Earth. Mass is typically measured on an electronic balance. You can also measure it on like a physical balance system. And it's typically measured in grams or kilograms. If you're stepping onto a scale that's in metric units, it's going to say kilograms, because kilograms are big. Kilo is 1,000 grams in a kilogram. Some useful relationships between units of mass include 1 kilogram is 1,000 grams. So this K is for kilo. Kilo equals 1,000. So in the metric system, all of the prefixes, the part that we're putting in front of our unit, so gram is the unit, kilo is the prefix, all of these mean a number. We'll see a table coming up that shows all of those. So kilo means 1,000 grams. So a kilogram, the kilo part means 1,000, so a kilogram is 1,000 grams. So that's a very useful relationship. Another useful relationship is that a kilogram is 2.205 pounds. And if you don't want to remember the 0.5 at the end, 2.2, close enough, because it's not exactly 2.205. So me, as a chemist who's taught a lot of chemistry and deals with these units all the time, in my brain, I think 2.2 pounds is 1 kilogram. And that's occasionally helpful for converting stuff. Do we have any questions so far? Great. I'm going to assume that means that I'm doing an awesome job. Sounded me patting myself on the back. Volume, the space, 3 dimensions, occupied by a substance, is typically commonly measured in liters. It's also measured sometimes in milliliters. So again, this milli part, this is our prefix. And this prefix means 1,000th. Or 1 over 1,000. So there's 1,000 milliliters, because they're really small, in 1 liter. Some useful relationships between units of volume include 1 liter is 1,000 milliliters. That's probably the best one to know. Also, somewhat relevant is that 1 milliliter is equal to 1 cm to the 3rd power. Does anyone know what that 3 means? This 3? Cubed, or raised to the 3rd power. It's the exponent of 3. So cm3 cubic, that's what the 3 means. Centimeters. Anyone play Mario Kart ever? Any Mario Kart fans? The speed that you select in Mario Kart, 50, 100, 150, sometimes 200 cc's. cc stands for cubic centimeters. So cc's is actually like the engine displacement for the motorcycles. Generally just more is more powerful, or for the carts. For cars, you'll usually see it measured in liters, so 1,000 cubic centimeters. But motorcycles still use cc's. Cars, typically you're going to see liters. So somebody's big truck, or their like whatever it is that has a Hemi Cuda in it, will tell you some number of liters. That's how much air the engine takes in, something related to that. I'm not a car person, but I think that's a fun connection. Cubic centimeters is the same as the cc's that you see in Mario Kart. And I think it's 3.76 liters. I'm going to add a little squiggle on top of that, equals. I think it's 3.76 liters in a gallon. $3.785. Sad. So 1 liter is similar in size to 1 quart. That would be our English equivalent. Sort of like a meter is similar to a yard, a liter is similar to a quart. They're not the same size, but they're close. They're similar. It's like if you ask somebody how tall they are and they say they're 6 foot, and you say, really, you're 6 foot? And they're like, well, I'm 5'10". Yeah, it's close enough, depending on your context. All right, so that was volume. We also have temperature. Temperature is a measure of how hot or cold an object feels. Is it hot? Is it cold? And we measure this with the Celsius scale in the metric system. Sometimes you'll also hear about the Kelvin system. Kelvin is just an offset Celsius. So we're going to think about the Celsius system. So like on this thermometer that's on this tree, yellow? No. I can't tell what color's good. Thermometer that's on a tree. We can see on the right side the degree F in the bottom right. So this is the units that we're used to. On the left side, the degrees Celsius, the units that we would use in the metric system. One way that I've heard these two described before, degrees Fahrenheit is how hot or cold we feel. So 0 is super cold. 100 is really, really hot. We get over 100 here, unfortunately. And so degrees Fahrenheit, how we feel. Degrees Celsius, how water feels. At 0 degrees Celsius, water's freezing. At 100 degrees Celsius, water's boiling, so that's really hot. There are different size scales, and there's also an offset. If you are converting between Celsius and Fahrenheit, you can memorize the formula. You can also just ask your phone or your web service of choice to do it for you. And then time. Time is based on an atomic clock that someone somewhere in the world, multiple people in the world have, and it's measured in units of seconds in the metric system. And you should know 60 seconds equals 1 minute. 60 minutes equals 1 hour. 24 hours in a calendar day. That's stuff that you've probably been using your whole life. Expect that to show up when talking about time. All right, so those are our domains, the things that we can measure, we can apply measurements to. We have base units, and I've been talking about prefixes, so we can combine our base units with prefixes. And this is where the metric system really starts to shine, is the prefixes. The prefixes can be used to note a wide range of measurements. So we can do really big numbers, we can do really small numbers. Some of these, if you're familiar with like computer storage size or phone storage size, you'll have already used some of these because we use them in computer storage. So first, the base units. We've got the different things that we can measure. We've got our unit names. We've got the abbreviations. I would recommend learning these. Learn/memorize these. These are just good to have in your back pocket. If you're measuring length, our base unit's meters. Meters is M. If we're measuring volume, our base unit is liters. L. We're measuring mass. You can also think of it as weight. It's not exactly the same. Kilograms, kg, or grams, g. And now a truncated, meaning shortened, we've cut off some of the ends, prefix table. So this is a not inclusive prefix table. So on the far left, we've got the prefix. This is the fully spelled out, what you would see if you wrote out the whole thing, like centimeters, centi. So centimeters, we've got centi, that's the prefix part. It has the symbol that follows after. So some of them are lowercase, some of them are uppercase. Most of them are lowercase. The lowercase, uppercase matters, and I'm going to point out. I don't think you'll need to know all of these.
Just for sure the ones before them. Like in the base, the slide before.
It would be great if you knew these. Okay, so I'm going to point out where the capitalization matters. This is why we need the capitalization is important. So if we take a look at mega, mega is our prefix with a capital M, big M. We also have milli with lowercase m. So if you get big M and little m confused, we're talking about very, very different units. So it's important when we're communicating with science, with our units, it's important that we get the symbol correct. And this gives me some chuckles sometimes because in the world of like food and beverage, the M is not always lowercase when it's supposed to. Sometimes it's uppercase. So you'll get a can of soda that says it's like 400 ml and it's capital M, capital L. It's obviously not 400 million liters, but it makes me chuckle a little sometimes. So this is where that capital lowercase is really important. The one weird one that I'll point out here is for micro. It's got the weird looking U. Notice it's got the little thing in the front. That's because it's the Greek for mu. Mu. So it's a U just with a little thing in front also. It's not really important. I'm just pointing it out in case you're curious about it. And then each of these prefixes means something. So mega means million, kilo means 1,000, hecto means 100, deca means 10, like 10 years is a decade. Deci is 0.1. And there's a mnemonic device for remembering the order of some of these. So starting with kilo working down to milli, King Henry died unusually drinking chocolate milk. So that's kilo, hecto, deca, unit. Drinking chocolate milk. Deci, centi, milli. And then everything outside of that goes in orders of 3. So milli is 10 to the minus 3. When we move one smaller to micro, it's 10 to the minus 6, nano is 10 to the minus 9, pico is 10 to the minus 12. And it works the same way moving up. So if we look at kilo, 10 to the 3, mega 10 to the 6, giga 10 to the 9, tera 10 to the 12. And you might recognize tera like in terabyte, giga, gigabyte, mega, megabyte. The same prefixes that we use for storage that we also apply in the metric system. So that's why I was saying some of us, we might know the relationship between some of those. I'm probably spending way too long in explaining this because I'm a chemist and I love units, and I'm used to lecturing a lot about this. So this is more information than you probably need. If you've got questions, let me know. But you should know the middle ones. The King Henry died unusually drinking chocolate milk, like the order of them. Okay, we also have equalities, two things that are equal. So equalities use different units to describe the same quantity. So you can measure stuff in meters. 1 meter is 1,000 milliliters. And in the metric system, these are all exact. There's no rounding or estimation. In our units of weight, the English units of weight, 1 pound is equal to 16 ounces. 2.205 pounds is 1 kilogram. 1 minute is 60 seconds. So these two things, 1 minute equals 60 seconds. So you can convert between the two. There's lots and lots of equalities that you can find out on the internet. You can also find them on food labels. So the contents of a lot of packaged foods are listed with both metric and US or English units. I think partly it's so that they can sell it multiple places. Nobody's confused about what the amount is. But this is going to indicate the same amount of substance in 2 different units. Like, for example, this can that's in the back here, net weight 15, that's probably ounces, 425 grams. So it'll tell you how much it is in the metric as well as in the English. So look for that next time you're looking at food, which is hopefully later tonight or tomorrow. Here are some conversion factors, some things that are equal, some equalities. This is not all of them, this is just some of them. Great news, you don't need to have these memorized. Most people don't have a lot of these memorized, and you would just look them up if you needed them. So this would be a good reference page. Something you can come back to in the future if you need to convert between things. Otherwise, typically, you can just look it up. Any questions at all about measurements, scientific notation, or units? Cool. Then keep reading the book. Chapter 1.6, this is like for the week. Get up through somewhere around 1.6. And then I forget what MLP stands for, but it's like mini lesson plan. One of our big overarching goals for the semester is the lesson plan project and presentation. There's a pre-flexion part, so you can find that assignment on Canvas. It should be up. If it's not up, message me and I'll put it up. So that's due Sunday night. So just sort of like, what do we think we might want to do is what's going to be on there.